Okay, so the next thing for us to talk about from this chapter is some vocabulary related to research methods themselves. All this number crunching we're talking about here in statistical analysis is what we do with the measurements we've made, but this is about, well, how do we organize and take those measurements? And there's two main types of research methods. And the first one you can see here are what we call correlational methods. Sometimes they're called descriptive methods. I try to not use that word because I don't want you to confuse it with the idea of descriptive statistics, although they absolutely connect. But correlational methods is what we'll call them. So if we are using correlational methods in our research, what this means is that we are going to measure two variables for every participant. So every person in our sample gets measured twice. So let's stop for a second and think about this word variables. A variable is a concept or a construct that can take multiple values. It's a condition that can change. The value can change from person to person, or the value can change in a person over time. Age is a variable. How old I am now is different than how old I'll be tomorrow. My age is probably not the same as your age. If we just say it a little different, variable. So it's an idea that's able to vary. It's able to take more than one value. So in correlational methods, we're going to identify two of those. We can say variable X and variable Y. And we measure each person just on those variables. Every time you measure a variable, if we take a variable and I measure one person, what I've gotten is called a raw score. So a raw score is a single measurement. So if we went back to the earlier example of surveys about what's your favorite flavor of ice cream, if I asked just one person, what's your favorite flavor of ice cream? And they said strawberry. That is a raw score. If I just asked one person, what's your age? And they said, I'm 24. That's a raw score. We usually just say score because we're kind of lazy and it's easier. It could also be called a datum, but that's weird. So most of us just say score, but a score or raw score is the measurement of a single variable. It's just one measurement. When we get all our measurements put together as a set, then we can call that data. So data it's a plural, datum, singular, raw score, data, plural. So it's a set of measurements. It's a set of multiple measurements. So for our correlational technique, we're going to identify two variables, variable X, variable Y, and we're going to measure them as they naturally exist. What is this person's score on variable X, and what is that same person's score on variable Y? Now let's go to the next person, and they get measured twice. What's their score for variable X? What's their score for variable Y? Go to the third person. What's their score for X? What's their score for Y? Until you've gotten your whole sample measured. Notice that what I said a moment ago, as they naturally exist, we're not trying to change anything. I'm not trying to look for a cause and effect. Does this one variable create changes in the other variable? We're just looking for patterns, correlation. A relationship between two, can be more than two, but we're going to say a relationship between two variables. Are they connected? Is there a reliable pattern that exists between them? Not a cause and effect, just do they happen to go together? So let's think about, we're going to go and measure people. I'm going to have you go gather a sample and measure some data. You're going to get a tape measure and you're going to measure how tall someone is. So one of the variables is height. They're this many inches tall. And then the other variable is going to be shoe size. We're going to get one of those little, it's called a Brannock device, one of those little metal plates when you go to shoe shop, put your foot in there and see what your shoe size is. Oh, you're a size 10 or whatever it is. So variable X is their height, how tall are they? Variable Y is their shoe size, how big are their feet? And we might ask ourselves, well, is there a relationship between how tall somebody is and how big their feet are? And of course the answer is yes. The taller a person is, the bigger feet they tend to have. The shorter a person is, the smaller feet they tend to have. Now it's not a perfect pattern, no pattern in our world really is. but it's pretty reliable. You don't see a whole lot of really tall people running around with little tiny feet falling over all the time. You don't see a whole lot of short people with clown shoes on, right? So what you have is a general pattern, a general relationship between height and shoe size. But it's not cause and effect. Nobody, I think, would feel sane declaring that having big feet caused someone to get tall, or being tall caused someone's feet to get big. Genetics and nutrition dictate those things. They're not cause and effect related, but there is a pattern there. And we can measure that pattern with correlational data. So that is one of the methods, the correlational method. We're going to take our participants and we're going to measure them twice, once for each variable as they naturally exist. Notice we weren't trying to make people taller. We weren't trying to make people shorter. We weren't trying to change the size of their shoes. No cause and effect. We just said, how do things naturally exist, and is there a pattern between them? Knowing that there's a pattern, again, is not the same as cause and effect. To assume cause and effect when we know that there's a pattern is called spurious reasoning. It's an error in logic. So if you said, oh, there's a pattern between height and shoe size, I now conclude that height causes shoe size. Again, that would be silly. But you and I and every other human on the planet, we are neurologically pre-wired to jump to that conclusion. So let's say that we decided we were going to meet for class, we were going to go out into the world, we're going to go to a park, and we're all going to socially distance and put our masks on, and we're going to do our lecture outside in the park. Okay. So you're sitting there and you're listening to me talk about statistics, and you're starting to feel a little hungry, and you notice not too far from you here in the park, there's a bush with some pretty red berries growing on it. You think, yummy. And so you pluck berries off of that bush and you eat some of them. All right, well, you're not hungry anymore, and they were kind of sweet and tart and good. 20 minutes later, your face turns blue and you fall over dead. What killed you? You want to say the berries killed you because it's a pretty logical assumption, but notice that's just a correlation. We don't really know for a fact what killed you. Maybe it was the berries, maybe it was something else. Maybe it was something you ate earlier in the day. Maybe you were born with a congenital heart defect that nobody ever knew about it, and it was just your time. That was just it, all done. There's no way to know exactly what caused you, but everyone else in the class is going to assume it was the berries. All of us survivors are going to look at you and go, don't eat the berries. It might be lethal. It's a survival mechanism. It's an evolutionary survival mechanism to assume cause and effect. We are built to do that. But in the world of science, we can't make that assumption. So there was a study released many years ago that showed that in countries where they consume a lot of green tea, cancer rates were lower than they are in the US. And of course, everyone who kind of got exposed to that, it was on TV and on the internet for a little while, this is many years ago now, a lot of people ran out to the store to go buy green tea, right? No one wants to deal with cancer if they don't have to, so let's try to avoid it with green tea. Well, this was a correlational study. All they said is we notice there's a pattern. If you're somewhere on the planet where they drink lots of green tea, those places tend to have lower cancer rates. Most of us assumed that green tea had an effect on cancer, but it doesn't. We don't really know exactly what it is, but it's probably lots of stuff. Lifestyle and environmental toxins and overall diet and exercise, and there's probably a bunch of reasons to explain why their cancer rates might be different than ours. You would have to do a different method that we'll talk about in a minute to know if the green tea caused a change in cancer rates, but it doesn't. And so that's another example of something we say there's a pattern, but we don't really know what causes it. We don't know why, only that the pattern is. In order to try to determine what's causing the pattern, we're going to have to go to the second type of research method, which we will address in the next video.